is another member of the NExScI family here at Caltech. I'm delighted to introduce David Ciardi, who is actually the Deputy Director of NExScI, and will talk to us about how do you put this all together, right? We've talked about how do you get a job, who are the people who are going to give you the money, and where do they get the ideas from, the decadal survey, and then how do you put the money ideas together to have a concept for a telescope, and then what happens when people actually put those concepts together. So I'll turn it over to you, David.
All right, thank you. Can everybody hear me okay? Thank you, Anjali. Thanks. Okay, so I wasn't actually going to talk about myself, but since everybody else did, I'm going to say just a few words about myself that's sort of relevant to the things that have been said. So a couple of things that came up during the early career or starting off your career panel was how do you what happens if you want to change your ideas or change your direction? And so I am a poster child of changing the direction that you want to do. I changed dissertations and advisors in graduate school in my 4th year. And I did my entire dissertation. It was an observational dissertation, 3 different telescopes. 1 was in space, 2 on the ground, and did my entire thing in 18 months. And so I don't recommend that to anybody ever. But my point is that you should not be afraid of change, right? Every kind of change is possible. You just need to be willing to take on whatever it takes to do that. And sometimes change is hard and sometimes it's easy. It becomes harder as you move along and take on more responsibility in your life and in your career. But you should never be afraid of taking on a bit of change if you think that's what you need to do for yourself and for your career, both personally and professionally. So don't ever be afraid of that. And the other thing I want to point out, a couple of things that were said is never be afraid to talk to other people or be nice to other people. Turns out that Keith and I were postdocs together at the University of Florida. We overlapped for, I don't know, 2 years or whatever it was. And then Keith went off to Goddard, and then randomly, 40 years later, I ran into Keith at JPL, right, or whatever it was, right? So never, ever be afraid to chat with somebody who isn't really part of your group. Just, you never know when you're going to run into them again. And then finally, and then I'll move on to what I'm actually going to talk about, Sarah had mentioned that your network isn't just the people who are senior to you, but also people who are your peers, or even who are even earlier in their careers than you. And again, I'm a poster child of that. One of my big changes that I made ended up because the spacecraft I was working on failed when it went into orbit. I had to make a change. What was I going to do? So I called up my closest friend from graduate school and said, "Great, I have a year to do whatever I want. What am I going to do?" And that actually directly led me to being where I am today. And randomly, I met Hannah, who's now at NASA headquarters, at some WS meeting. I actually had to ask her 3 months ago, how did we meet? And she had to remind me. I didn't remember at all. I had gone up to her. She'd given some talk as a graduate student, and I went up and chatted with her. And now, yes, she's at headquarters and I'm at NExScI, but we're colleagues. And so never, ever underestimate the power of just being nice and chatting through with the groups, because you never know who you're going to end up working with. All right, so this talk was kind of a weird talk for me to put together. A few weeks back up at JPL, I had given some kind of talk that I was asked to, and it was sort of basically talking about some older missions that had gotten developed, and the technology and how that had moved forward and how we're seeing it now here. And that then prompted Anjali to ask me to give a talk of how did we get to where we're going today, which is trying to talk about the development of the Habitable Worlds Observatory. And so this is actually this is where we want to get to. This is currently, I don't remember where I stole these figures from quite anymore, but some kind of giant 6-meter telescope that has to get to contrast levels so that we can get to an Earth-sized thing and an Earth-like orbit around a sun-like star, so that we can get some kind of spectrum, right? And there's an entire set of work that's going on right now to define what this thing needs to do, how big it needs to be, how sensitive it needs to be, what kind of spectrographic capabilities it has to be. But this didn't just happen. It wasn't like the 2020 decadal woke up one day, panel woke up one day and said, "I know, we need to build a 6-meter telescope that can get to the right contrast level so we can do a spectrum of the Earth." This has been a long time coming. And so this talk is actually an overview of a bit of that long time coming. And I really actually want to, I'm up here talking, but I actually really want you guys, Chaz Beischman is in the room, and Chaz has been a strong mentor to me and to Dawn and to a bunch of other people in this room over the years. And so while Chaz and I have lived through almost everything that I'm about to talk about over the last 30 years, Chaz has actually lived through it longer than I have because he's older. I'm also 12 years old. So, all right. So when did this all actually really begin? So there was a call early on in the late 80s and early 90s. This actually came out of the Solar System Exploration Program, which doesn't actually exist anymore because NASA redefined how the directorates, science directorates were put together. And coming out of the Solar System Exploration Program, there was a desire to understand how do we get to literally towards other planetary systems or TOPS. If you're going to Google TOPS, NASA TOPS today, what you get is the Open Science Program, right? So they stole an acronym from 30 years ago without recognition of that work. And I will say that this program from the late 80s and published in the early 90s in 1992 has actually laid the foundation for everything that you're going to talk about today or this week in terms of direct imaging and trying to get to a place where habitable worlds will actually detect an Earth-sized planet. So the TOPS program actually has 4 main things that it recommended. I'll go through some of this. First, starting on the ground. That's not too surprising. That's very often what we do. Then some kind of moderate mission to do some work, a larger mission, and then actually a lunar-based imager. And I don't actually talk about the lunar stuff in the rest of this talk, but I do want to point out that there's an entire lunar program that is being developed in partnership with our commercial partners. And there's an opportunity beyond HWO to really start thinking about putting something on the surface of the moon. And I can talk about that ad nauseum if you really wish. I can talk about probably anything ad nauseum if you really wish. So I do want to point out, excuse me, I do want to point out though that and this is something that actually every speaker today has alluded to, that we as scientists and engineers are not doing this in isolation of the rest of the universe. And in fact, a major shift happened in the early 90s that really has enabled us to have this journey over the last 20 or 30 years. And the 2 things happened in the early 90s. First, a meteorite, which had actually been discovered in the early 80s, had been found in Antarctica. And it had been determined that it had likely come from Mars, that there was some kind of impact on Mars. The rock landed on Earth. And then a bunch of Greek people had done some work on a slice of the rock and determined that these fossilized remains were likely fossilized microbial life that had likely come from Mars. Turns out that that's probably completely wrong, right? Fair enough, that's how science works. But at the same time that also is happening, 51 PEG had just been announced. And so now we have discovered a planet around a sun-like star, and there was talk about microbial life starting on another planet in our own solar system. And this actually got the community outside of our own community stirred up and excited about the possibility of life elsewhere. And President Clinton actually made an entire speech. You can go find it on YouTube. That's where I did that screenshot. I can't believe it's on YouTube, unbelievably. So where he talked about this and about setting us on the path to determine whether or not there was life outside of the Earth, both in our solar system and outside of our solar system. And this is what enabled the development of going from a report like TOPS that said, hey, we should do stuff, to actually enabling the agencies to say, hey, let's put some money into this and do stuff. And that's exactly what happened. So the very first thing that they started off with was the ground-based program. So this enabled scientists and the astronomical and the astrophysical community to make the argument that the Keck telescopes are an ideal ground for which to start this program and to do a bunch of work on the ground in search of planets and on this path to finding Earth-like planets. And so NASA bought into the Keck partnership. That's actually what funded a big part of the second telescope. Excuse me. Apologies. And that's what funded the second telescope and enabled Keck 2 to be built. And this partnership, NASA's original plan was that it would build a set of smaller telescopes around the two larger telescopes. They would connect the 6 telescopes together. They would do high precision astrometry, and they would be able to measure, astrometric orbits of planets at like the 2 to 3 microarcsecond level. So this would be giant planets around nearby stars. This plan actually got fairly far along in terms of like there was hardware built, there were telescopes that were designed and purchased, but without getting into the history of the Keck interferometer, in the end, this project never came to fruition. The one thing that did come to fruition with this was the interferometry between the two very large telescopes, the two 10-meter telescopes, and they built a 10-micron knowing interferometer. And the goal of that was to measure the excesses of radical dust around nearby stars, connecting to like a lot of the work that Keith was talking about that he did as a graduate student, as a postdoc, bringing our knowledge about our own radical light and connecting it to what we might see around other stars. So while in the end, the astrometric program didn't happen, the Keck partnership did produce a set of observations that were incredibly important for helping us move forward in our understanding of the effects of zodiacal light. And actually, much more importantly, that Keck partnership continues today, right? So this came out of something 30 years ago where a report was written that said, hey, we should do astrometry on the ground and find big planets. And now, as a community, we have access we have public access to the most spectacular telescopes on the planet. And I think Jason's here this week. Is Jason here this week? So Jason's famous plot of thank you. I'm blanking on the star. 8799. Thank you. Good Lord. I'm getting old. Anyway, right. This came out of partly came out of NASA's contributions to the telescope, and of course, all of the planet discoveries that HIRA's had done. A big chunk of that happened because NASA contributed to the CCD upgrade that HIRA's underwent in the early 90s. My point is not to talk about Keck as a whole here, but to show you that you never know exactly where you're going to go and how you're going to build, and laying out the plans can have unforeseen benefits and consequences going forward. But we really did start down the road of trying to find Earth-mass planets around nearby sun-like stars, and there was a mission called the Space Interferometry Mission. And this, again, came directly out of the TOPS program. This was the next recommendation in that report, which was basically build an astrometric mission, put it into space, and survey the nearby stars and find the Earth mass planets in the Earth-like orbits. And SIM, started its development in the late 80s through the early 90s. At the time, it was called the Astrometric Imaging Mission, but it changed and evolved over time. And these were simulations that were done as part of trying to understand what kind of precision that you would need in a mission like SIM. SIM was a 10-meter baseline. It would do micro arc-second precision. And it probably would have had the ability to discover 50 or 60 Earth mass planets within the neighborhood, within about 50 parsecs. Unfortunately, it didn't survive the. Sorry, let me go on the next thing. So, in partnership with SIM and following on to what SIM would have discovered was the Terrestrial Planet Finder. So Terrestrial Planet Finder, or TPF, you'll often hear TPF actually had two concepts. One was a chronographic version, and one was a free-flying interferometry version. The chronographic version would have been worked in the optical. The free-flying interferometer would have been in the infrared, and that would have been in partnership with at least the European Space Agency. They were calling it Darwin at the time. And this was the second major part of the recommendation of the TOPS report. It was, work from the ground, find the planets with astrometry, and then go get spectra. And we would have done this in both the optical and in the infrared, so you can piece together the different pieces of the atmospheres. And so these went fairly far along in what I would call PowerPoint designs. SIM actually had, the Space Interferometry mission actually had a full-fledged test bed, and we were building hardware at JPL. But the 2010 decadal came along, and it basically said that we actually don't want to do SIM and TPF. They basically canceled them in an unceremoniously in a footnote in that document. It's actually kind of hard. You have to actually go search for it if you go look at that document. It's quite interesting. But what they did say was that they really wanted to concentrate more on the science and the technology development, because they didn't think at the time that we knew enough, both scientifically and technologically, to be able to do the work that we needed to do in order to go and image an Earth. And so rather, they wanted to concentrate on the demographics and the characteristics of the planetary systems. And it turns out, at that same time, Kepler had just launched, right? So Kepler was launched in 2009. And so by the time we were writing this up and this report came out, Kepler had barely released its first 300 planet candidates. We had barely published our first 5 planets, right, coming out of Kepler. And standing here in 2024, we can all probably look back and just recognize the sheer shift that Kepler produced onto the scientific community just by the sheer number of planets that Kepler discovered. And so the other part that they recommended was a demographics mission with WFIRST. WFIRST stood for the Wide Field Infrared Survey Telescope. Basically, this is the microlensing experiment that they said you should go off and you should do microlensing and figure out what the frequency of the outer solar systems are. And that's what the decadal in 2010 recommended that we do. Not the least of which was, oh yeah, by the way, finish JWST and get it launched. But then an interesting thing happened just a few years after SIM and TPF were canceled and WFIRST was selected as being the next flagship, is that NASA ended up in a partnership with the National Reconnaissance Organization, or NRO. Basically, they said, hey, we have this 2.4 meter telescope that we're not using. Do you want to use it? And that changed Roman from just being a microlensing mission of, it's going to do this wide field survey, We're going to go find a bunch of microlensing planets and determine the frequency of Jupiters in the outer solar system or Marses in the outer solar system to, hey, this telescope is big enough that we can actually add a coronagraphic imager to it. And so Roman all of a sudden became something that was now along the same path that TOPS had originally talked about. And so while that was all being developed, more concepts were still continuing to be developed. And in the late, or a few years after the 2010 decadal, there were two concept studies called XOC and XOS, which stand for chronograph and star shade. And this was the first time that the concepts had been organized in quite that way. What do you need to do to get to an Earth-like or an Earth-sized planet? But then they also introduced the concept of what the star shade might do. And yes, while the star shade is not part of the architectural discussion for how the world's going forward, it's still a viable technology that might come into play after HWO is launched, or maybe even as a secondary instrument to HWO at some point. And then, of course, as Tiffany described the entire process, one thing that she mentioned was the development of the concepts for HabEx and LUVOIR leading into the 2020 decadal. So what NASA headquarters had asked the community to do was, look, what do we need to do to detect an Earth-sized planet around a sun-like star? And those two concepts are what the decadal sort of smushed into one to what has become where we are today, which is trying to decide what Habitable Worlds Observatory is. And so this is a long process for which it didn't just start with this concept or what came out of the 2020 decadal. And so as Anjali is ready to rip me off the stage, I just want to end with some final thoughts that's part of this. And that is that we've been on this march for at least 30 to 40 years, let alone the philosophical approach of trying to understand who we are and where we came from since the dawn of humanity. But this very specific path that we are on was laid out in a report that was put together 30 years ago, and we were still on that path. And so when Tiffany or Hannah or whoever talked to you about getting involved and being engaged in something today, this is the kind of long-term impact your thoughts and your ideas can have. And just because you're early on in your career doesn't mean that you can't have a contribution. And in particular, you'll eventually be standing up here talking to the next set of generations, talking about how old you are and how long that you've been doing this. It's been a series of technology developments that have carried forward beyond the initial missions that they were originally intended to support. So we did a bunch of work for Keck and TPF and SIM and for HabEx and for LUVOIR and XOC. And all of that technology development is still what we're building on today and a big chunk of what you're going to talk about this week during the workshop. I still want to point out that masses are still a challenge. And we're trying to do this from the point of view of EPRV and astrometry. And it would not surprise me that if astrometry needs to come back, and that if we fly something like SIM or we do astrometry with HWO to get the masses, that will likely have to happen because the RV is so hard. And that will only happen because we have built upon what we've done for so long. And just as a note, for those of you who are listening, if we had flown SIM, we would know exactly where to point HWO today. We wouldn't have to use HWO to go find the planets. We would have already found them. All right. And then finally, I just really want to end with that it's today's science that leads to tomorrow's missions. So just because you're not doing something that's exactly relevant to imaging or exactly relevant to RV or exactly relevant to whatever, doesn't mean that your science isn't part of the periphery that we're putting together. It's all part of the same collective community ecosystem that we're all working towards. And you should never, ever be bashful about changing your direction if you so choose. Thank you.